Hello students, welcome to Our Classes, and we will be solving the Iiser entrance test paper for the year 2018 over here. The first question that was asked over here, the melting point of Mn4n is what? This is basically a memory based question, okay? And here the answer directly I would like to mention is higher than that of the manganese metal. More conceptual question is question number 17. Which of the following statement is valid for the dipole moment of cis and trans F2N2? So the structure of F2N2 cis trans, which are basically geometrical isomers, is as follows. Okay, this is the lone pair on nitrogen, and for the trans, we will say this is the structure, and we know that the electronegativity chi of F is greater than chi of N. So when we have to write the bond polarity or indicate the dipole for the NF bond, so obviously it will be directed towards the F in the manner shown over here. Okay, so now over here what we will say is that both these dipoles of the NF bond are in the same side, so for which we will have a resultant dipole moment mu, say NF, for the cis. Okay, however, if we consider the dipole moment of the NF bonds in the trans molecule, then we can see they are lying in opposite direction. So out here the mu NF resultant for the trans will be equal to 0, and a similar thing can be said for the resultant lone pair moment also. But out here for the cis mu NF resultant dipole moment, we will say this will be not equal to 0, and hence we can say that the mu value for the cis F2N2 will be greater than the mu value for the trans. Okay, and that should be our correct answer. Question in 18 is, which of the following statements is correct about the tetrahedral manganate and permanganate ions? So let us draw the structure for manganate and permanganate ions, or if you just write the formula, this is the manganate ions. Okay, MnO4 2 minus is the manganate, and MnO4 minus is the permanganate. So this is your manganate, and this is your permanganate. Now if you calculate the oxidation state over here, say this is X and this is Y. So if you calculate, what will you see? For each of this oxygen over here, it is carrying -2 charge. There are 4 such oxygen, so it will be equal to 4. So out here we will say that X -8 -2 equal to -2. So X out here is coming out to be +6. For this one, permanganate, if we calculate, so we will have the algebraic equation Y -8 similarly, and that will be equal to -1, and we will say Y is equal to +7. We know the electronic configuration of Mn is basically Ar 4s2 3d5. So when the oxidation state of Mn is +7, we will say it is basically a D0 system, and when the oxidation state of Mn is +6, then it is a D1 system. A D0 system will be what? It will be diamagnetic. It will be diamagnetic. So we will say this is our diamagnetic, and the system having D1 electronic configuration will obviously, we will say it will be paramagnetic. So having considered these facts, and we know that the manganate is green in color, whereas the permanganate is purple in color, and all these colors are due to ligand to metal charge transfer transition. Ligand to metal charge transfer transition. Okay. So out here we will say that the manganate will be green in color and it will be paramagnetic, and hence the correct option over here is going to be C. In the next question, we have been asked. Okay, let's go to the next page. Among the lanthanides EU, TB, ER, DY, which one readily forms a stable divalent ions? Now this can be answered if we consider the electronic configuration of these elements. So out here for EU, what we will say, it is basically xenon 4f7 6s2. All right, this is for EU. Now for TB, what it is xenon 4f9 6s2. If we say for DY, it is Xe 4f10 6s2, and if we consider ER, it is Xe 4f12 6s2. Now if we were to consider the +2 oxidation state for each of these elements, then for TB, what we will able to see, it is Xe 4f9. For dy +2, it will be Xe 4f10. For ER, it will be Xe 4f12, and for EU 2 plus, it will be Xe 4f7. And what we can say further is that out here, this electronic configuration is half filled. Okay, and so has extra stability due to exchange energy. Okay, but all the other cases, as we can see, they are not half filled or completely filled, rather incompletely filled. What I mean by that, your 4f9 is incompletely filled, your 4f10 is incompletely filled, and 4f12 is incomplete filled. That means they are not stable, and hence answer over here will be EU, because it has gained some extra stability because it is half filled configuration. Okay, next question over here given is to find the correct order of decreasing basic strength of the molecules PH3, ASH3, SBH3, BIH3. Now what we can say over here, that basic strength of P block hydrides, okay, decreases down the group. And why does it happen? What we can say over here, the reason is down the group the elements use pure p orbitals for bonding to hydrogen. That means the S character of available lone pair increases, and we can say as the S character increases, the basicity decreases. And that is why I said that basic strength of the P block hydrides over here, the group 15 hydrides decreases down the group. So we will be considering BiH3 to be the least basic and PH3 to be the most basic, and so over here the correct order should be order B. Question number 21 is given in the following reaction sequence. We have to identify the products. So over here we have been given CH3NH2, alright. But what is important to consider over here is this nitrating mixture okay, sorry, this nitrating mixture is basically acidic. Now because it is acidic, out here what we will say, this NH2 group will get protonated. Now what happens when this NH2 group gets protonated? If this is having a lone pair and that is taking up say one proton, then in the mechanism what we can say is this type of an intermediate will be formed within the reaction mixture, and this has minus I effect, or rather we can say it is an electron withdrawing group NH3 minus. So basically it deactivates ring and is meta directing. So if you are using or generating nitronium ion, which is the electrophile over here, this is basically our electrophile. This reaction is nothing but, over here the reaction is basically aromatic electrophilic substitution reaction. Okay, this is an example of an aromatic electrophilic substitution reaction. So what we will say is the CH3 group will promote via electron donation or via plus I effect. It will want the electrophile to come over here. Similarly, the NH3 group also will allow the or want the electrophile to come in the meta position with respect to it. CH3 will want the groups to come ortho or para position, but the para over here is already blocked, as we can see, so it will only enter the para position, ortho position, and hence the structure that we will get, or I should say the product that we will get, will be this type. So this is the major product that will be formed over here. In the next question, which is also basically aromatic electrophilic substitution eventually, but in the first reaction they have given CH3COCl. This is a acid chloride given to us, and we have a NH2 group. So over here N-acetylation will take place. That means this CH3 is here. We have a Cl. So the lone pair will attack here. Eventually that opens up, giving a minus charge, which will again now come back. Once it comes back, this Cl will go away as a leaving group. Okay, so basically out here our product that will be formed will be basically the N-acetylation of paratoluidine. This compound is called paratoluidine, so it will be basically NHCOCH3. So this is what is formed. Interestingly, this compound again is being treated with concentrated H2SO4 and HNO3, which is again the same nitrating mixture. So what is going to happen is CH3 is having plus I effect, but this group, because it is having a lone pair, it will be showing plus M. We can call this as moderately activating, but it will be a much more powerful electron donating group in comparison to CH3. Okay, in comparison to CH3, this is much more powerful. That means when electrophile comes, so when we have NO2 coming, it will be directed to the ortho position of this group. It will be directed to the ortho position of this group. Okay, as we can see, the para position over here is blocked. So that means what we will say is the product, that is the Z out here, is going to be having the structure like this: NO2, NH, COCH3. So this is my Z and this is my X. Okay, having said that, if you try to identify now from the given options, so we can see the only option that is matching out here is going to be the option D. So this is out here, this is our correct answer for the X and Z. Alright, this will be the correct answer. Next question. Question number 22 says, select the correct order of basicity for the following compounds. Now out here, to find out the basicity order, the thing that we need to remember is basicity depends on availability of lone pair. Okay, we will say decreases with the increase of S character. Okay, this is point number 2. So when I said availability of the lone pair, I mean to say that resonance decreases availability, or delocalization of the lone pair decreases availability. So if we judge the S character of the lone pairs given over this nitrogen, this nitrogen is having sp2. Okay, this is also having sp2, this is having sp2, but this is having sp3. And what we have learned so far, that basicity decreases with the increase of S character. That means sp3, or we can say lone pair on nitrogen sp3 will be more basic. Okay, sp3 is more basic than sp2, which is more basic than sp. So obviously out here compound number 1, from here itself we can say, is most basic. There is no doubt about it. So we got to look for the option in which 1 comes first. As we can see, only option B has 1 coming first. Okay. Now if we compare pyridine and diphenyl amine, out here what we can see, in a pyridine, this lone pair is in the sp2 orbital. Okay, and the p orbitals are perpendicular to the sp2 orbital carrying the lone pair. Okay, so this is at 90 degree. That means no delocalization possible, or no resonance possible. So it means the lone pair available. But if you look at the lone pair of diphenyl amine, what will be clear? Okay, suppose this is the H and that is again. So out here what will be clear, that this lone pair, okay, at any moment, if I say this is the alignment of the p orbitals of one of the phenyls, and we have the lone pair in this alignment, okay, again these are in this alignment. So in short, what I'm trying to say is that these lone pairs can be delocalized to these phenyl rings, okay, generating set of new resonance structures which can be written as follows. Okay, which can be written as follows. Okay, further this can go here, that can go there. So basically we can say that these lone pairs over here, they are delocalized and not available. It means what? My pyridine, that is molecule number 2 should be more basic than molecule number 4. Okay, that is what we can understand. Besides that, besides that, we can say negative charge is more stable on oxygen than nitrogen. If that is the case, we think, then what we can say for this particular structure, okay, there is this lone pair which can get delocalized in the manner I have shown. So most of the times we will say that the negative charge is on the oxygen, okay, or this is having a good amount of contribution. This structure is having a good amount of contribution. That means this lone pair is heavily conjugated over this oxygen, so it is least available, and that is why, and that is how we can explain this order. As one is greater than, we will say one, which is this, greater than this one, which is greater than this one, and which is greater than the amide. Okay, that is how we can explain this order. Next question is 23. Which of the following is a correct pair of intermediate possible for the formation of X and Y as the major products in their respective reactions shown above? So, if we do the mechanism, we can understand easily. Over here we have CH3, CH2, and it is undergoing addition to HBr. This is basically, we will call this as electrophilic addition reaction. So what is the electrophile out here? That is the H plus, and Br is delta minus. This is my pi bond. So the pi bond will be attracted towards the H plus. What it means, basically, out here two set of cations can be generated, which is as I have shown here. This is 1 degree and this is 2 degree, so this is more stable, and eventually Br will add to this. So this is a 2 degree carbocation that is formed, and this is the more stable, and we will say this is major, okay, and this is major, so this is minor. So eventually the addition of Br takes place in the second carbon, and this is the product that is formed. So obviously it is going via the major carbocation, which is 2 degree carbocation. Okay, now what about this one? We have explained the first one. The next one is basically peroxide effect. All right, and out here what is going to happen? Let's have a look. This C6H5 C double bond O, O, C double bond O, C6H5. Under the influence of light, it basically breaks like this to give you C6H5 C double bond O dot. Okay, that is what is formed. Now, this molecule, when it reacts with Br, it will take up one of the H as a radical, generating Br dot radical. So over here in this reaction, we will say 6H5COOH plus Br dot radical. So this is the initiation process. Now what is going to happen because of this? CH3CH double bond CH2, when it meets one such Br radical, there are two electrons over here, so they will join, and the propagation step happens in which the radical is formed on the middle carbon. So this is, we can say, a 2-degree radical that is formed. Eventually this will take up one H dot, and the product that we will get is going to be CH2, CH2, CH3, CH2, CH2Br. And normally this product is being called as the anti-Markovnian product. Okay, so over here we normally call this product as to be the anti-Markovnikov PDT, because this is lower degree alkyl halide, and this one is called the Markovnikov product. Okay, so out here from this we can say that D will be the correct option over here. Next, again another organic question in which we have been asked to explain, in the following reaction sequence, identify the relationship between the products Q and S. Okay, so over here we have been given, so let's do the mechanism, that way it will be easier. CH3CH2 C double bond O H is being reacted with CH3 MgBr. So this will make a nucleophilic attack on this. Okay, and this will open up like that, and here it is MgBr. Now if you treat this one with H3O plus or H2O, basically it only forms a alcohol which is of 2-degree type. So this is my P out here, please understand. Now then they have said we are removing or using H2SO4 and heat. So basically here E1 elimination will take place. The previous reaction, that is this one, is basically the nucleophilic addition reaction using a Grignard reagent. Okay, this is my Grignard reagent. So out here what is going to happen? Whenever there is a OH and you use acid, okay, so consider this, okay, as a hand rule. There is a OH group, it can be attached to anything. It can be a carboxylic group or it can also be a alcohol. So suppose you give H. What you do is basically you protonate. After protonation, OH now becomes a beta leaving group because plus charge on the oxygen is not stable. Now this will cleave away and it will produce this particular carbocation which I have shown here. With respect to this carbocation, we can see there are two alpha positions which is here and there. Now what can happen out here is any of under these reaction conditions any of the hydrogens can be moved away. So if you remove this hydrogen, that is one possibility, we say A, or you can remove this hydrogen, that is another possibility, we say B. But in both the cases, okay, it will basically lead to the formation of a more stable alkene. So out here if we compare CH3, CH double bond, CH3, okay, or we can have another possibility which is CH3, CH2, CH double bond CH2. So this is coming from elimination of B hydrogen and this is coming from elimination of A hydrogen. Now this particular compound is more stable. This is more stable. Why? Because it has more alpha hydrogen. Okay, this has around 6 alpha CH hydrogen. 6 alpha CH hydrogen, and this one is having only 2 alpha CH hydrogen. So obviously this is more stable, and this is our Sedgef product. Okay, this is our Sedgef product, and this will be our major product. So over here our major product is what? Q. This one is our Q. Now we have given another reaction, so let's do that too. So we have been given acetone. All right, we have been given acetone. So say out here this is the acetone that has been given, and it is treated with CH3 MgBr followed by this. So basically it is going to lead to the formation of this alcohol, which is our R. If we treat this with H2SO4 in presence of heat, again water gets OH gets protonated, water will be left away, and out here this type of a 3-degree carbocation will be formed, which will lose this proton like that, and eventually the product that will be formed is going to be having the structure something like this. And if we compare this structure, which is obviously S, this is our S with Q, S with Q, okay, if you are comparing this S, all right, with the Q, then we will say these are basically structural isomers, and hence our answer is going to be option A. Okay, next question number 25 says arrange the following compounds in the increasing order of rate of reaction towards hydroxyl ion. So this is basically from the topic of aromatic nucleophilic addition, okay, elimination reaction. All right, now this type of reaction theory is a rate increases with the presence of electron withdrawing groups at ortho para position. If we now compare with respect to chlorine, there is one ortho here, one ortho there, and one para. So this will be the showing the maximum rate. Okay. When we have to compare between ortho and para, because ortho is near minus I effect will be more. So ortho will be more than that of the para. From the meta position, only minus I effect operates. Okay, only minus I effect operates. But from the ortho, okay, from ortho we will have minus I and minus M both operating. Okay, here also we have minus I minus M all operating. But why is ortho winning? Because distance, with distance minus I reduces. Okay, we will say ortho nitro chloro chlorobenzene more reactive than para nitrochlorobenzene because of the nitro group in the two being near to Cl shows greater minus I effect. Okay, that is the reason. So what should be the order then? Obviously, over here we will say 1 will be greater than that of 2, which is ortho. Ortho will be greater than that of the para. Okay, and for meta only I is operating. Okay, there is no minus M, so that should be the least one, and hence the order should be C out here. Okay, let's consider the next question over here, in which